Today we start series, chapter 11, section 2. It will be presented in several pieces. The first part is the general concepts. So we are going to see a little bit what is the series and what type of series we have. Series is just an infinite sum of terms. So I have this symbol here of summation. It's a special one because we start with the index 1 and then we go to infinity. So it's not a finite sum, it's an infinite sum. And then we add all the members of the series. So some of the examples, for instance, we can have a series that looks like this. So here for k equal 1, we have 1 over 1 plus 1 over, for k equal 2, 2, 1 over 3 plus 1 over 4 plus 1 over 5, and we keep going like this. So this is a series. This member here is A1, A2, A3, A4, A5, etc. So some of the series that we will see will be convergent, which means that the sum is equal to a fixed number, and some of them will be divergent. Another example, let's say a series like this with 1 over k squared. So we have this, then 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, and then we keep going. So some of the series are convergent, meaning this sum here is a finite number, and other series are divergent, which means that you don't get a finite number. So this series here is called harmonic, and it is known to be divergent. We don't need to prove it, we know it, and this series here is convergent. Later on we will see what is the value of the sum of this series. What we know also is if I multiply a series by a fixed number different from 0, the fact that the series is convergent or divergent will not change. So for instance, if I have a series 1 over, let's say 3 to power k. So this series, later on we will see that it is convergent. 1 over 3 to power 3, 1 over 3 to power 4, then we keep going. Right? If I multiply this series by a number, let's say if I have a series 7 times 3 over k, so this seems similar. Oops. 1 plus 7 over 3 to power 2, 7 over 3 to power 3, 7 over 3 to power 4, etc. So obviously we see that we can factor 7. It would be easy, and then we get the previous series. So whatever happens regarding the convergence of the previous series, when we multiply it by 7, convergence remains the same. So this is 7 times the series 1 over 3 to power k. So if this series here is convergent, then this series is convergent. And this one here will also be convergent. Obviously, here this series, harmonic series, is divergent. If I multiply it by 5, well, the resulting series is divergent also. So in these cases, situation is clear. Maybe one of the useful results, we have something called P series, similar to P integrals. essentially we have 1 over n to power p, and when p is smaller or equal to 1, then the series is divergent. And when p, the exponent here, is strictly bigger than 1, then the series is convergent. We don't need to prove it. We use this result. So essentially, this will be something that we will use often, especially later on. Let's try to put the power properly. It doesn't work. Okay. So we don't need to prove it. Obviously here when p is equal to 1, we have our harmonic series. We know it's divergent. And when p is bigger than 1, then the series is convergent. For instance, here we have exponent 2, and we know that this series is convergent. Later on we will see the value of this series also, the sum. So those are some of the general terms in regard with the series. We have some other types of series. So P series is one of them. Another one is called geometric. So geometric series, essentially we have an argument, and then we have common ratio R to some power. So essentially what we have here is something like this. So we have terms, so common term R, and then we have the ratio that is put to different powers. And we will see in which conditions this series is convergent. So just to go straight forward, if we have this ratio that is strictly smaller than 1 in absolute value, geometric series is convergent. And when this ratio is bigger or equal to 1, the series is divergent. Now the good news about geometric series, this is one of the rare cases where we have actually the sum when the series is convergent, and the sum is given by an expression. So S sum, it is the first term A, the argument, divided by 1 over R. So that's when the series is convergent. If the series is divergent, well, then we don't have the sum. And there is another type of series called telescoping. So one example of such a series, I'll just give one. Later on we will see how to deal with this. So this is telescoping series. Some of them are convergent, some of them are divergent. This particular we will show that it is convergent, and we can find the sum of this series. So that's general situation with the series. One more important result is that to find the sum of the series, to determine if the series is convergent or divergent, we have a special procedure in cases where we are able to compute. So when the series is convergent, so the series in question is equal to some number called sum of the series. And how do we get this sum when the series is convergent? The sum is equal to limit of partial sums. What is a partial sum? Essentially, partial sum is just certain number of terms that we add. So instead of going from 1 to infinity, we go from 1 to n. Okay. So let's say if I go back here, and use this series here, general one. So S1 would be the first term A1. S2 is A1 plus A2. S3 would be A1 plus A2 plus A3. S4 is A1 plus A2 plus A3 plus A4. So you see that these partial sums, partial because we don't add everything, we just add one piece. So we get a sequence of these partial sums. When this sequence is convergent, converging to a fixed number, then we say the series is convergent to that number. If this sequence of partial sums is not convergent, meaning that we don't converge to a fixed real number, then we say the series is divergent. So we will see one or two examples with this, especially when we deal with telescoping series, how it works. And that's important because the definition of the sum of the series is given here, and it means it is a limit of partial sums. So if this limit here exists, it's equal to a fixed number, then we say the series is convergent and we have the sum of that series. If this limit does not exist, then we don't have the number and we say the series is divergent. Now, how can we have the limit that doesn't exist? Well, maybe these partial sums are increasing to plus infinity or going to minus infinity or oscillating between the numbers. So essentially, as long as these partial sums are not going towards a fixed real number, we will say that this limit does not exist and therefore the series will be divergent. When the limit exists, we say the series is convergent.